Welcome to the Space Nanotechnology Lab at the MIT Kavli Institute. Here, researchers are creating new technologies for the next generation of X-ray telescopes that will be launched into space. X-rays are produced by some of the most energetic objects in the universe, like exploding stars, enormous galaxy clusters, and the accretion disks of black holes. The Space Nano Lab is developing ultra-thin mirrors to focus X-rays and better diffraction gratings to split up those X-rays into their different wavelengths, like an invisible rainbow. These nanoscale technologies will help astronomers see farther into the universe than ever before.
The Space Nanotechnology Lab was built back in the early 90s, specifically to fabricate a few hundred diffraction gratings for the Chandra X-ray telescope, which is one of NASA's great observatories. It's basically the Hubble of X-ray astronomy. The experience gained during that time has been leveraged by the director of the lab, Mark Schattenberg, over the years to continue developing technologies so that future missions will be much more powerful. So my main responsibilities are in the area of diffraction gratings, X-ray diffraction gratings. Some of you might wonder what actually is a diffraction grating. It is basically a very regular structure. It's a sequence of lines similar to the teeth in a comb, for example. It acts in a somewhat similar fashion to a prism, even though the underlying principle is different. You can send light through a grating, and on the other side comes out a rainbow. For X-rays, it is more challenging because the wavelengths for X-rays are much shorter than the wavelengths for visible light, and therefore the spacing of those teeth of the comb, so to speak, has to be much finer.
So that's bars that are about 50 to 100 nanometers wide that are 4 to 6 microns deep. So that's a very high aspect ratio structure. And fabricating those is very challenging. X-rays are absorbed in the atmosphere, so all of X-ray astronomy has to be done in space. So that makes things tremendously more difficult because now you're building, a payload on a rocket. You only get one chance to do it, so you've got to do it right. You can't go and fix it once you launch it. So we're trying to come up with all these creative ways on how to fabricate an efficient structure out of silicon that's strong enough to survive space launch and deployment and in-space survivability for many years.
So now you have the grating and it generates a rainbow of X-rays. So what that tells you is when you look at a source, what kind of X-rays does the source emit? You can tell what element has generated an X-ray of a certain wavelength. So by looking at the wavelength of these X-rays, we can tell a lot about the abundance of different elements in the source, how hot the source is, and this tells us a lot about the physics that are happening at these sources. A big focus of our current work is to improve X-ray mirrors. X-ray mirrors have the function of a lens in an X-ray telescope. X-rays are very hard to transmit through a lens and to refract like you do with a traditional lens and visible light. Instead, X-rays need to be reflected at very shallow angles. It's very similar to skipping a rock on a lake. If the angle gets too high, the X-ray doesn't get reflected, it just gets absorbed. And so X-ray optics consist of many mirrors typically that are stacked inside each other, and in order to be launched into space, they have to be very densely packed, and therefore they have to be very thin. So thin and flimsy, just holding them in order to measure their shape is a problem. So imagine putting up a large potato chip of about this size on its edge, and it sags under its own weight enough to change its shape so that it can become a problem.
The most different thing our lab does compared to some other labs is that we take on a project completely sort of by ourselves. It's good for personal growth because you take a lot of responsibility and you learn a lot of things like in the process.
Nanofabrication is just very interesting. You're trying to build things in this world that you can't see optically, so it's kind of like you have to use tools and infer things to do your building. We find that exciting, so we really just enjoy the hands-on nature of what we do.
Our laboratory environment was like a playground. I just get in, look for something, grab something, and build something that I imagined. And if it works, I'm very happy. If it doesn't, I go to Mark and Ralph, discuss what I think about it, and work again and build something that's useful. Our group has been here for about 40 years. So a lot of hardwares and softwares, knowledges are accumulated. That was a great part of my experience at MIT working here, which is very different from other groups.
Mark gave a talk at a conference entitled From Nanometers to Gigaparsecs. And I think that really sums it up quite nicely what we're doing in our lab. We're working at the smallest scales with the highest precisions. And what we're trying to do is build instrumentation that allows us to look at objects from basically the other side of the universe and to learn about the structure of the universe itself on the scale of gigaparsecs, which is a significant fraction of the known universe.
I'm starting to gain more understanding about why this is important. Just looking at the vast universe, thinking how small we are, I think I'm very humbled by that idea. And I feel that I'm contributing a little bit by working in this project. It's a tiny part of a very big project, but I feel I'm making an impact.